Today we're going to look at the second derivative test as a means for calculating an extrema. Now let's review what we've learned thus far. We have learned thus far that extrema will always occur at either endpoints or critical points. Now they could also occur at an endpoint and a critical point, but this is where extrema always occur. And we've learned how to find the extrema values by two methods thus far. We've learned the candidates test, and that's where we identify the candidates, which are endpoints and critical points. And then we substitute them into the original equation to determine which values are the greatest and the least. Now the second technique we've used to calculate the extrema is the first derivative test. So again, we calculate those critical points, and then we make a sign chart of the first derivative, and we look at the signs, right? And we learned that if the sign changes from positive to negative, because if we look at the motion, it's going positive and then negative, then that will give us a maxima. And if our first derivative sign chart changes from negative to positive, then we know the motion goes negative to positive, so then therefore we have a minimum. Now today we're going to learn about one more technique for calculating an extrema. The last technique is called the second derivative test for finding or determining actually whether a point is a max or a min. So what we'll do is we'll always first find that critical point. So we'll set the derivative equal to 0. And if at that point the second derivative is less than 0, that means our graph is concave down, then we will have a local maximum. How does that work? So we have a critical point. We know that extremas occur at critical points. And if its second derivative is negative, remember our little faces? So the second derivative is negative, we know the graph is concave down. Well, if you look at this sad face here, and you look at the extrema, when a graph is concave down, you can see that it is a maximum. Okay, now the same rule, but just with different signs, applies for minimas also. If you find a critical point where the first derivative equals 0, and then you also notice that the second derivative is greater than 0, that means we're concave up. Okay, second derivative is concave up. Then at this point, your value will be a minimum, because if a graph is concave up and you have a maxima or a minimum, and you have an extrema, let's say, it must then be a minimum. Okay, so if you read these explanations here, they'll help. If a critical point happens to occur in an interval where the graph of the function is concave up, then that critical point is a relative minimum. And also, same goes here, but if the graph of the function is concave down, then that critical point is a relative maximum. So we're revisiting again the resource page that we have for first and second derivative test, and we're talking about a new technique for determining whether a critical point is a maxima or a minima. So again, we first identify the critical point, and then this is the piece that we didn't talk about earlier. Now if the second derivative at that critical point is negative, you have a relative maxima. And if the second derivative at that point is positive, you then have a relative minimum. Okay? So, and remember, of course, our little warning, or not warning, but just don't forget, on closed intervals, check the endpoints, because they can also be extrema. Now let's do an example. So we're given a function, and it's a nice polynomial. And this is when I tend to use the second derivative test. So if we take the first derivative, because we're going to identify critical points, we get 3x squared minus 6. So we know this first derivative is a quadratic, and we know that if we set it equal to 0, we're going to get two candidates, okay? So we set this equal to 0, we factor out the 3, so we get 3 times the quantity x squared minus 2. So then we know when we set that equal to 0, we're going to get x equals positive radical 2 and equals negative radical 2. Make that negative a little bigger. Now, according to the second derivative test, we've calculated the critical points. Now, if we look at the second derivative and substitute those values in, we can determine whether the values are max or mins. So the second derivative here is 6, whoops, I'm sorry, the second derivative of x, not of 6, there we go. Second derivative of x is going to be 6x. So the second derivative, when I substitute the critical point radical 2, I get 6 radical 2, which is a positive value. And then if I substitute the other critical point into the second derivative, I get negative 6 radical 2, which of course is a negative value. So therefore, since the second derivative is positive, that means if it's positive, we have concave up. So therefore, we have a minimum at radical 2. So at x equals radical 2, there is a minimum, and this is how you would justify it, since f prime radical 2 is equal to 0 and f double prime radical 2 is greater than 0. And that's an excellent justification. Now for negative radical 2, we notice that it's negative. Well, if the second derivative is negative, then we have located a maximum. So again, I would rewrite the sentence above, but I would say at x equals negative radical 2, there is a maximum, since f prime at negative radical 2 is 0, and f double prime at negative radical 2 is less than 0. And that is our example. Now one last thing we're going to clarify. And the last thing that we're going to clarify is just some verbiage regarding increasing and so forth, because sometimes this can be a little bit confusing, and I'm hoping that this might help your understanding. Now we're looking at f of x. And if we want to determine if f of x is increasing, we have two techniques. We could look at the actual function, right? And so you can see here, my y values are increasing. So therefore, the function is increasing. So f of x is increasing if the values of f of x are increasing. Now when we look at a table view, we can see also between -3 and -2, the y values are increasing. Now I'm not quite sure what's going on in this area between -2 and 0, but then after 0, greater than 0, we can see again that we're increasing. So we can look at the values. Now we've also learned, according to the first derivative test, that if the first derivative is greater than 0, we can say that f of x is increasing. And we can clearly see that. We notice here the values of y are increasing. And so when we look at f prime of x, and we look at this section here, f prime of x is greater than 0. And then we also notice here that the values are increasing of f of x. And when we look at the f prime chart, the f prime values are greater than 0 in that same interval. Now we can apply this same logic to f prime x and its relationship with f double prime x. So what we can say is that if we want to determine if f prime x is increasing, okay, then we can look at the values of f prime x. And if they are increasing, then f prime x is increasing. So we can see on this interval that the values of f prime x are increasing. Now, if you don't have a graph of f prime of x, then you can look at the second derivative of x. And if the second derivative of x is greater than 0, which just means if the slope of f of prime x, right, you guys? So if the slope of f prime x is positive, that means f prime x is increasing. So if you look right here in this interval, from 1 to infinity, we can see that f double prime is greater than 0. So we can also say f prime of x is increasing if f double prime is greater than 0. Because honestly, the definition of concave up is that the derivative of x is increasing. Well, that's it for tonight. We'll see you tomorrow in class.